Let's compute the Cook's distance and see if we can improve the model by removing the extreme observations. We are working on the California school dataset, CA school. Let me start by importing the dataset. Split into training and test data in the ratio of 75% to 25%. Then I am renaming the rows of DF train to start from row number 1. This is useful for identifying the correct rows after you have computed the Cook's distance. We will use this later on. Now let me build the model. We have seen this model before. This is yielding an adjusted R square of 80.22%. Now let's try to find the Cook's distance from this model. But before that, let me compute the evaluation metrics. On the test data set, we have a MAPE of 0.01047. It's very small, but then there is a certain amount of error in the data set. All right, now let's compute the influential points. If you plot the Cook's distance using influence index plot, the plot that I am interested in is on the top, the very first plot over here. Here you have the Cook's distance on the y-axis. X-axis is the row indexes. This is first row, second row, third row, and so on. You will have as many vertical lines as there are observations in your training data set. As you can see, there are certain observations that are having a very high Cook's distance. By default, it is marking 253 and 273. You can pick more observations if you want. You can even select these two as influential if you feel so. Even these observations can be considered as influential if you feel after inspecting from the dataset that this could be an extreme point. Now let's compute the actual Cook's distance. It is contained in CD. The actual values of Cook's distance is actually very small. It is in small scale. So how to identify the extreme values, extreme points? Any Cook's distance value that is 4 times the mean of this vector, 4 times the mean of CD, those observations we are considering as influential points. Now all the influential points is in this particular vector IPS. The names of each item in this vector is the row number of the training data. So 43 means that is the 43rd row in df underscore train, and the respective Cook's distance is marked here. Top rows will now contain the row numbers of those points. And these are the Cook's distance. These are the most influential points. Now, next step is to rebuild or retrain the linear regression model by excluding those points. From df train, I have excluded these top rows. Now, if you look at the model summary, we have an adjusted R square of 84.65. This is certainly an improvement. Previously, we got an adjusted R square of 80.22%. Now that's 4% increase. But you cannot really compare these two directly because we have lesser number of data points in this data set. Even though it is not directly comparable, it seems like we have definitely improved on how we are explaining the y variable in the data set. Now let's predict on test data. Let me note down this new MAPE that we are getting. Now we have 0.01039. Previously we got something very similar, 0.01049. So the difference is in the fourth decimal. We have 0.01039. It is a very small improvement, but if you consider we are already having a accuracy of 99%. What I mean by accuracy is 1 minus MAPE I am calling it as accuracy. We are having a very highly accurate model. Any improvement that you can make on this model is going to be in very small scale. So this is a significant improvement considering that we already have an accurate model.